Hi, welcome back. Today we're going to be talking about the magnetic force and also magnetic torque, or torque due to the magnetic force. This is going to be video 2 of this week's videos. This one's going out a little bit late, but that's okay. So let's just get right into it. This is the problem that I picked for us to do today. It's going to be utilizing cross products, a little bit of integrals. So hopefully this will be helpful for you all, but let's just get right into it. Let's read the problem, and I'll underline some buzzwords that I see. So it says, a uniform bar of length L carries a current I in the direction from point A to point B. The bar is in a uniform magnetic field that is directed into the page. Consider the torque about an axis perpendicular to the bar at a point A that is due to the force that the magnetic exerts on the bar, that the magnetic field exerts on the bar. Part A says, suppose that an infinitesimal section of the bar has length dx and is located at a distance x from point A. Calculate the torque d tau about a point A due to the magnetic force on this infinitesimal section. Then part B says to use this equation, which I'm going to rewrite, to calculate the total torque on the bar. And then C says show that tau is the same as though all of the magnetic force acted on the midpoint of the bar. So let's start first with our coordinate system, because that's going to be very important for that. So it says that I'm going to say that this is our x direction, because we have our we're going to say that our origin is something like this, like right by A. So that's our x direction. And then since basically what we're doing is we're just tilting the axis, I'm going to say that the y direction looks like this. And then our z direction is coming out of the page like this. Like that. So cool. Now we have our axes. So let's kind of define what what we know. So we know that this bar, I'm going to say that it has length L and it's a vector. And this vector is pointing in the x hat direction. So I'm going to call it L x hat. And actually, we could call it big L x hat. Well, let's keep it just L x hat for now. And then our B field says that it's a uniform magnetic field that's directed into the page. So the way that I have it set up right now, I have Z, the positive Z direction is pointing out of the page. So since our magnetic field is pointed into the page, we're going to say that our B field is in the Z hat direction. Let me actually rewrite this. I'm just going to kind of say L is in the X hat and B is in the negative Z hat. So what we first want to find is we're trying to find our d tau in the first part. But if you remember from 141, torque is actually just it is a relationship between the radius of some object, like how far away this force is, and a force. So if you remember, tau is torque and is defined as R cross F, and those are cross products. Or we could say that it's R F sine theta. So that's one definition, but we want to find F first, because we're trying to find the d tau due to this magnetic force that is being exerted from the magnetic field. So the equation that we use for that is F wire is equal to big I L vector cross B vector. And similarly, you can say that it's ILB sine of theta, where theta is the angle between your vectors your vectors L and B. It's important to note that in this specific case, the current is constant, and that is what you're mostly going to be seeing. That's all you're going to be seeing. You're going to be seeing a constant current through your wire. So when we think about how to find our forces and stuff like that, and when we are going to be eventually integrating, we have to think about what is changing throughout our problem, and current is never going to be one of them. So there's that. So let's start with A. So A says, suppose that an infinitesimal section of the bar has length dx and is located a distance x from point A. Calculate the torque d tau about a point A due to the magnetic force on this infinitesimal section. So the first thing we should do is find the force that acts on this dx, which is right here. I'll erase this so that we can see this a little bit better. So dx is right there. So the first thing we want to do is find the force on that part. So, and more specifically, our df. Because if we're looking at this, the one thing that's not changing in our torque is our length. So this radius thing right here is not going to be changing, but our force could be. So let's find our df. But firstly, let's go back to our little drawing right here and think about our axes. That's x, y, z. So what is special about our length vector and our B field vector? They are at 90 degrees with each other. They're perpendicular with each other. So if you remember from the video I made on cross products, that is when things are perpendicular to each other, that means sine of theta is equal to 1. So really, this F on the wire just becomes ILB, since sine of theta is equal to 1, because the sine of 90 is equal to 1. So now we have to think about our df, and we have to think about what is changing in our equation to find the df at this particular dx. So it already says in the problem that it has a current I. So we know that it can't be I because it has a constant current I, and that is going to be true most of the time. B says that it's a uniform magnetic field, so that's not changing at all either. So the only thing that we're left with is L. And maybe that was a bit obvious for some of you because it has dx in it, like that is what we're going to be using. But if you weren't so sure, that was the only thing that we're left with that isn't a constant thing. So our df can be written as I dl b, or since we are given a actual value dx, let's write it as I b dx. Okay. So now that we have our df, we can talk about our d tau, which equals r cross df. Now, the reason why I chose r to be the same is because we are at this distance x. So our r vector is actually x hat. And if we remember our force, we didn't talk about our force. So what direction is our force going to be in? Well, when we did our cross product, we know that our L vector is in x hat. Our B vector is in negative z hat. And I'm going to use a trick that I outlined in the last video, which is this trick using unit vectors. So if I want to find what x cross negative z is, I'm going to start at x. I'm going backwards to z. So that should, if it was a positive z, that would say that we would get a negative y. But we have a negative z. So a negative and a negative equals a positive. So L cross B, or in this case, x hat cross negative z hat, is equal to y hat. So our df is in y hat. Now, what about tau? So now we're left with our r hat, which is that x value, this x value right here. And then we have our df, which is in y hat, and we found what our df is. It's going to be this right here, but it's in y hat. So we want to find what r cross df is. So since we have unit vectors again, I'm going to do the same trick again. So x, y, z, all in a line like that. So then we go x hat cross y hat. There's no negatives involved, so we get z hat, and that's going to be what our d tau is going to be in. So I'm going to write that down, z hat. So since we are in, it's also important to note again that our r vector and our df vector are going to be perpendicular. So just like how this I wrote ILB sine theta, we can write r df sine theta, where the sine of theta between the r vector, which is this x value right here, and that dx, df and df are perpendicular to each other. So this sine theta equals 1. And we're left with that d tau is equal to r df in the z hat direction. Now, what is r? R is how far away the distance between where the force is and where our in comparison to the origin. So I'm taking that our origin is at A, and we're trying to find the d tau at a part dx. So my distance from our origin to that dx is x. So we have x, and then df is IB dx. And that is our d tau, and it's in the z hat direction. Okay, so then part B says, use this equation, which I'm going to rewrite, to calculate the total torque tau on the bar. So we have this equation right here, d tau equals x I b dx. So if I want to find the total torque on this, to find the total torque on the bar, then I want to say I'm going to integrate this side and integrate that side. When I integrate over here, d tau, and when I integrate over d tau, I get left with just tau. And now we have a equation on the right-hand side to find the total torque. But it's important to note our bounds. So our bounds is in terms of x. So an x goes from A to B, and the total length is L, big L. So I'm going to say that our bounds are from 0 to big L. I and B are constants, so we can take them out of the integral. So I'll take those out and say 0 to L x dx is our equation to find tau from 0 to L. And now I'm going to use the power rule to do the integral. So I'm going to say that it's IB, and then we want to add one more and take the numerator down to the 1/2. So if you're confused, we have right now we have we have x to the 1. We have x to the 1. We're going to add 1 to it, so we get x squared. And then when we bring down the x squared and we put it to 1/2, so that if we took the derivative, we would get x. That's just the power rule, just a quick aside. So then we have that it's IB x squared from 0 to L. So then we have IB, and it's L squared minus 0 squared. So 0 squared goes away to 0. And we are left with that the tau is just IBL squared in the z hat direction. It doesn't lose its directionality when we integrate over it. Sorry, I made a mistake. It's 1/2 IBL squared. I forgot the 1/2. Put that right there, 1/2. Again, right here, 1/2, because we integrated over it and we did the power rule. So now let's do part C. It says, show that tau is the same as though all of the magnetic force acted on the show tau is the same as though all of the magnetic force acted on at the midpoint of the bar. So we know that our total force is, going back up to this, we changed it a little bit, but we still have this FIL cross B. And we already decided that L and B are perpendicular, so the sign between them is just 1. So sine of theta equals 1 in this case. If we wrote ILB sine theta, this goes to 1. So they're left with F equals ILB. If we want the total force of what this magnetic field is giving us, it would just be I capital LB, because that's the total length of our vector that we have. So that's our force. Now we want to find the torque at the midpoint of this bar. So our torque is defined as R cross F. Again, they're perpendicular to each other, so we can say that it's just RF. But this time our R is L over 2, because that's the midpoint of the bar. So it's L over 2. And then we have our force, which is ILB. And if you check, we would get that it's 1/2 IL squared B, which is exactly what we got over here. And again, it's in the z hat direction, just like before. All right, so I hope that was helpful. Please reach out to me if you have any questions. And yeah, I hope you have a great rest of your day.